Yeah, good afternoon, one and all. It is our great honor to introduce our distinguished keynote speaker, Akihiko Sugiyama. With over 40 years of experiencing in developing telecommunications, speech, and audio signal processing systems, Mr. Sugiyama is a renowned expert in his field. He has contributed significantly to international standards and holds in numerous patents. His expertise spans international standards such as ISO, IEC, MPEG, audio, ITU, and 3GPP, where he served as interim chair of the MPGO audio subgroup, bridging industry and academia. He has 25 years of teaching experience and has supervised 75 interns, with 5 research engineers earning advanced degree under his guidance without formal enrollment. He holds 273 patents, 6 trademarks, has contributed 17 book chapters, and has received 23 awards. He has delivered 205 invited talks in 95 cities across 31 countries and is recognized as a fellow of IEEE and IICE. Additionally, he has served as a distinguished lecturer and industry speaker for IEEE and was honored as a rockstar speaker by the IEEE Consumer Electronics Society in 2020. His contribution also include serving on a key IEEE committees, including the IEEE Fellow Committee and the IEEE RSC James Clerk Maxwell Medal Committee. So today, Mr. Sugiyama will share his invaluable insights on personal information devices, portable to wearable, standalone to connected, player to sensor. His presentation promises to be an engaging and enlightening experience, offering practical tips and expert advice in this field. Please join me in warmly welcoming Mr. Akihiko Sugiyama to the stage. Welcome you, sir. Welcome for the keynote speaker.
Is it good? Oh, sounds better. Okay. So I'm going to talk about the personal information devices. This is actually a history. And, well, people say the fool learn from experience, but the wise learn from history. So that's why this is one of the reasons why I talk about the history, so that you will become wise. Let me start with how you enjoy music today. That is basically this way: you have a smartphone that is your own, and it is connected to your earbuds in your ears. And then there is an app. I don't know which one you use, Spotify, Apple Music, Amazon Music. You have one of these or maybe multiple of these, which are all connected to their central offices through the internet. And this is how you enjoy the music today. You don't have any dedicated player today in your pocket. So let me talk about the technology which enables this. That is audio coding. Audio coding is a technology to compress the size of the audio data. So this is an analog signal, which is usually expressed like this. This is a typical sine wave. This is a time axis. This is the magnitude or the amplitude or the power. And then it is first sampled. Sampling means chopping along the time axis, and then quantized. Quantization means chopping along the magnitude axis, so that the resulting signal can be expressed simply by a set of zeros and ones. So this is what is called a digital signal. So audio data compression or audio coding is a process to make the size of or the number of the CDs or any recording media, or the number of chips, or the size or the recording capacity, to make it smaller. That's the meaning of audio coding. So the resulting data occupies much smaller number of the chips or smaller areas of the chips, or the capacity in these days, or the smaller number of disks when it is stored in a disk, or more than discs. What made this technology possible was chip capacity, that is the capacity available on a single chip, one LSI, versus the data size needed to provide sufficiently good quality of audio signal. So that is the data size after compression. So it keeps going, declining with time. In the 70s, 80s, 90s, the data size after compression for sufficient audio quality kept declining. On the other hand, the memory capacity on a single chip kept increasing. So naturally, there should be an intersection like this, and which made it possible to perform full digital implementation of such a player. In early 90s, an international standardization for audio data compression started that is performed by ISO IEC JTC 1/20 SC29, which is usually called MPEG, or Moving Pictures Expert Group. So there are multiple phases. The oldest one is called the MPEG-1, which was finalized in early 90s. The major applications of MPEG-1 was these things, but the largest application was game terminal for TV receivers. In those days, the displays were too expensive for ordinary people to have at home. So usually people used TV receivers as the display at home. So this system is to convert signals so that it will be displayed in a TV receiver. For that purpose, we needed data compression, not only for audio, but also for video signals. The next international standard after MPEG-1 is called MPEG-2, which had more applications like this. And then it continued, not only for gaming terminals, but it made electronic cinemas possible, and the interpersonal communications like Zoom, WebEx, and Google Meet. All these things are based on one of the MPEG audio standard. And then following that year, there was MPEG-2 AAC, which is still in use for TV broadcasting, terrestrial TV broadcasting systems in Japan and Latin American countries. After following MPEG-2, we had so-called MPEG-4. MPEG-4 was developed for mobile terminals, including the smartphone handset. Well, in those days, we didn't have even a smartphone, but a mobile phone handset without a display, large screen on it. So the bit rate, or the size of the audio data after compression, was much, much smaller because we had to carry the terminal in the pocket. So these are possible applications when we standardize MPEG-4. Actually, it was the case. We have MPEG-4 in personal computers, SLR cameras, camcorders, and digital cameras, smartphones, old style feature phones, and even large screen TVs. Everything is benefit from MPEG-4 audio standard. And then there was yet another standard called HEAAC. HE stands for high efficiency. Naturally, it means its efficiency is much higher compared to the original MPEG-4 AAC. AAC, by the way, stands for advanced audio coding because it was the most advanced technique in those days, late 90s. So this standard is still in use in your smartphone to transmit or download or streamline the audio signal. It was used in independent audio players represented by iPod and smartphone terminals. So it was developed for audio players and smartphones, as I said, but its catch is half the bit rate compared to MPEG-4 AAC for the same quality. So the resulting data size is only 50% of it. It's twice as efficient as MPEG-4. Now, this shows a history of MPEG audio and audio standardization starting back in 1980 or 88, more specifically, following MPEG 1, 2, and 2 BC. BC means backwards compatible, and MPEG 2 AAC, most advanced standard, and then MPEG 4, its descendant, and so on until early 2000. Applications started early 2000, first to ringtone musics, and later TV broadcasting systems, terrestrial and the satellite. It actually started with the satellite TV broadcasting systems. But even earlier, in the time of MPEG 1, there was an application, mostly in European countries, for satellite digital broadcasting to cover multiple countries with multiple languages. And then in mid-90s, we developed the first all solid-state audio player based on MPEG technology. It was made available in the commercial market by other companies in late 90s. And then finally, Apple released iPod in 2001. So I will talk more about it in later slides. So let's look at conventional audio players until 1990. Long time ago. It started with Sony's Walkman. It was released in the market in 1979. It was the first personal entertainment because it was not possible until Sony's Walkman to carry your personal music system outdoors. That was a great invention. However, everything was implemented by analog signal processing. So naturally, it was suffering from noise. It is based on the cassette tape strategy, where the recording media is magnetic tape equipped in a certain cassette so that you can exchange a cassette to change the magnetic recording media. After that, there were CD players. CD players were all digital. That is a big jump from all analog implementation of Sony's Walkman. And the bandwidth, which roughly represents the quality of the audio signal, was 20 kilohertz. That was sufficiently wide. Plus, random access was possible because it is based on a circulating disk technology. Mechanical movement, however, was in place, and it causes skips of the music by shakes and vibrations. That was a major problem with that. Slightly later than CD players, there was yet another audio technology called DAT, or digital audio tape. It is similar to the cassette tape system, but the size of the tape is much smaller. It's much smaller than your palm size. However, it lacks the random access capability. It is based on the magnetic tape. You need to wait for some time to rewind it or fast forward it. That was a big drawback in those years. So when you look at these old technologies for personal media players, the problems can be summarized as the weight, too heavy, the size, too bulky, the power, the batteries that did not last for a long time, and also reliability. These were typical problems. And then, as I already talked about, there was an intersection between the recording capacity or storage capacity on a single chip, single LSI chip, and small enough data size after audio data compression for sufficient audio quality, there is an intersection. So that's why audio player with semiconductor memory. This is a potential solution for all these four problems. And that's why we developed a silicon audio terminal in 1994 for the first time in the world. This shows a brief block diagram, what is done in the system, but I don't think you are interested in something detailed like this. Let me talk about the memory capacity versus recording time. So the horizontal axis represents the memory capacity on a single chip. And then the vertical axis represents the recording time in seconds. I put some colors to show some typical recording time. This is 30-minute line. This is the 60-minute line. This is the 90-minute line. When you look at the horizontal axis, the typical memory size in those days, this is 32 megabytes. And this is 64 megabytes. This is naturally 128 megabytes. Today, what's the size of your smartphone memory size? That should be 128 giga, 256 giga. Somebody may have 512 giga or even 1 tera, right? So that's the size. When you look at the size here, they are just 3 digits smaller compared to what you have today. That represents the advancement of the technology in the past 25 to 30 years. So let's look at the typical bit rate, the typical size of the audio data after data compression. That is 96 kilobit per second. That means you have 96,000 zeros or ones every second. That is the size after data compression. When you applied this compression ratio, the recording time for the 32 megabyte memory card was, look at this, only 24 minutes. Very short time. Nobody will be happy to have some recording capability up to 24 minutes. That was the best we could do in mid-90s. How was the quality? How was the quality of the audio signal? It was actually fairly good. The vertical axis represents the score, which directly corresponds to the signal quality. Of course, 5.0 is perfect. So this is the quality. This level is the quality of the signal without any data compression. That's the original signal. If you apply data compression, naturally, the quality becomes lower and lower depending on what kind of method you apply, what kind of algorithm or standard you apply. So I am showing three different coding algorithms from MPEG-1 technology. This is called MPEG-1, Layer 1, Layer 2, and Layer 3. Layer 2 was actually one of the most popular ones. Let me concentrate on Layer 2 quality of the signal. After compression and decompression at a bit rate of 128 kilobit per second, that means you have 128,000 zeros or ones every second. The quality along this metric is 4.6 or something like that, very close to 5. That means the quality after data compression and decompression is very close to the original signal. So everybody is satisfied with it. The quality was really good. When it comes to 96 kilobit per second, as I explained in previous slides, it is still good. It's something like 4.3 or 4.4. It's far better than 4.0 and close to still 5.0. So the quality was good enough. And then that's why we try to prototype a working system in 1994. This is the version we developed in early 1994. This is a second version developed in 1994. actually in November or December. And then this is a later model in 1997. You can easily see that this is the bulkiest one. This is sufficiently small. This is much smaller. By the way, this is a memory card in those days. The size of this memory card is equal to your credit card. And you may also say it's the business card size. So you can have a brief idea of how big it is. What we did is to insert this card into this player so that the data can be transferred to the system, decompressed, and then it was possible to listen to the recovered music with the earphones. In those days, of course, those earphones are connected with wires. Because it was too early, we had general purpose LSI in it. The system was bulky. We didn't have any time to accommodate batteries in it. We had to supply the power from outside. That's why we see two holes here, which were used to supply 15-volt power and also 5-volt power, two different voltages. The second version was smaller. We developed a dedicated LSI chip for decompression. So that's why it becomes much smaller, as I will show you how it looks inside. It accommodates batteries in it, and then it became much smaller, mostly due to the advanced batteries. So because everything is implemented by digital signal processing, and there's no moving parts in it, whatever you do, you can jump, you can run, you can jog, whatever you do, there was no vibration which distorts the signal. So you can always carry your audio player, whatever you do, like this. So that was the biggest catch of this system, of this prototype. So this is a brief block diagram of the decompression or decoding system. There were actually two LSIs. One is called the bitstream decoder, and the other one is a general purpose signal processor. General purpose signal processor is a signal processing dedicated computer. You can control the chip about the task by writing a code. So it's just like a computer, but it does not accept any high-level language. You needed to write a very low-level machine language to make it work. Bitstream decoder was a half-programmed chip, so you cannot have big freedom compared to signal processor. So this is the whole system. Here is the board, and here is a card interface. You had the memory card here, and you had the analog signal processing part here, but you can easily see that the number of components is very small. There are not many parts when you, as far as you look at this schematic block diagram. This is how it is composed of when you look at the first generation silicon audio. This is a picture, a top view. This is a bottom view of the first generation. Here is a general purpose signal processing chip. This is slightly bigger than your thumbnail. And there are some additional chips here. This space on the other side of this board is dedicated to the memory card, which is in the credit card size. This slide shows specifications of the silicon audio player, the first generation. The bitrate was 96 kilobit per second per channel, and implementation was performed by one digital signal processor and a gate array chip, which is half programmable. The arithmetic is 24 bits, and then the size is 127 by 28 by 33 millimeters. If you had the 16 megabyte memory card, it could keep up to 12 minutes audio signal. If you had 32, you can put 24 up to 24 minutes. However, the problem in those days was that the biggest memory size was only 40 megabytes. So you could not record more than 24 plus minutes in those days. It was not possible because memory was not available. Now, this is the second generation. The difference is here. We developed a dedicated LSI chip. I was working for NEC, and NEC had the semiconductor division, which was big in those days. So it was possible to develop a specific LSI chip. So we developed one for decompressing the audio data. That's why it looks much simpler. Most of the major components include the memory card, this dedicated LSI chip, some additional controllers, small RAM, D2A conversion, and an analog amplifier. It's very simple. And when we look at the specifications, it's the same. The only difference is the size. Now it's much smaller. And, when you had the 32 megabyte memory, and you could record up to 24 minutes. These are the features. Because we had the dedicated chip, we also made it possible to decompress the next standard, that is MPEG-2. But otherwise, it's almost the same thing. The power supply was 5 volt. It was much easy because we didn't have to have 15 volts. That is a big advance. The chip size was very small, much smaller than your thumbnail, with 100 pins around the chip. The power consumption was 200 milliwatts. This is a photomicrograph of the chip. If you look into the chip inside and keep magnifying it, you see something like this. It's always true. If you extract one chip from your smartphone and open the package, try to keep enlarging it, you will see something similar to it. This is how it looked. And this is the exterior. It's slightly bigger than your thumbnail, but the inside chip is much smaller. Now, these are the pictures of the second generation silicon audio. On the left-hand side, I'm showing a top view. On the right-hand side, I'm showing the bottom view. This is, again, the size for the memory card, which is in the credit card size. This is the newly developed dedicated audio decoding chip, which performs decompression of the audio data. So let me talk about the challenges towards successful product, because those silicon audio models were just prototypes. They didn't go into the market. It was not that easy to develop a product, because there are many other things you need to consider to put one thing into the market. The first thing, this is actually the most serious problem, was that the memory price. In those days, 1 megabyte EEPROM is one type of erasable memory on the chip. It was $30 US, 1 megabyte. So if you had 32 megabyte, it should be 32 times of this price, which is too expensive for ordinary people. However, it was a good thing that there was a continuous price decline. And then this price decline made it possible for some startup companies to develop audio players and to put them into the market. The first company in the world to put such an audio player into the market was Sehan Information Technology in Korea. And other companies like Diamond Multimedia, Digital Cast, Raincom, blah, 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 mostly from Asian countries. In Singapore and Korea, they followed. And further, they were followed by typical Japanese consumer electronics companies like Sony, Aiwa, Toshiba, Matsushita, today, which is now Panasonic, and Sanyo. They all follow these Asian companies. The second issue we had in those days is copyright protection. If you let simply the data or the compressed data go, nobody can get money from the users. So that was the problem. So it was the case for most of the companies to negotiate with the companies who have the contents. It is always useful to have only one contract which can be applied to all the companies. However, it was very difficult because the situations were different from a company to another, and they have different requirements. Sometimes there was in-house competitions. For example, when you look at Sony or JVC or Japan Victor Corporation, they had in-house contents department, and they also have a consumer product department. So they also have to talk with the in-house contents divisions, which further delayed the negotiation process. And then Apple came up suddenly. Apple didn't take the same way. They tried to negotiate with one company and then try to extend it to other companies. One-on-one strategy was the way Apple took. And then, as you know, Apple was the success. Apple got the success, and the first to succeed, one-stop shopping was what Apple provided as iTunes Music Store, which is today known as iTunes Store. And then there was content distribution issue. In those days, the compressed media was not possible. All you had to do is to get the original audio signal, like compact discs, uncompressed one, and then you will feed the data into your software encoder or software data compressor in your PC and copy the data, which is the compressed audio signal, into your own memory. So this process was a kind of complicated one, and it was not easy for everybody to do it. So all these issues were the hurdles for the personal media players to become majority in the commercial market. So this slide shows the decline process of the memory price. In the year 1990, it was very expensive. In mid-90s, like 1995, the price for 1 megabyte was about $10 to $12. That was in mid-90s. When it comes to mid-2000, look at this. It is 2 magnitudes smaller compared to this one. That means 1/100, only 1% of the price here. So in 10 years, the price declined by 100 times. That is a drastic decline, as you can see. When it comes to 2010, you can see how cheap it is. And now it was possible for ordinary people to have memory-based terminals. So this is what we predicted when we developed that prototype, actually in 1994. And it just followed. This is our prediction, and it just followed our prediction to reach this level. Okay? Because it was revolutionary, it was reported in different magazines and newspapers and radio programs and even TV programs. This is one of those appeared in the magazine, New York Time magazine, which was the most popular one, issued in the US. They had a picture of this system and had some explanation about this development. It also appeared in in the cover page of a magazine issued in UK. It says goodbye CDs question because of this terminal, because of this personal information device. And the answer is clear now. We don't need a question mark. We have already said goodbye to the CDs, and even further, we have already said goodbye to independent, portable players, because everybody today enjoys the streaming music. Okay, so this is the article about the Silicon Audio in the Time magazine in 1995. This is the future music issued in UK. And the answer is clearly chip music after these years. Now, these pictures show the third generation, which is much smaller. This is the credit card size. The terminal, the player itself is much smaller compared to the old ones, mainly due to the size of the battery. Battery is much, much smaller now because it was made much smaller to be used in mobile phone handsets. So everybody worked hard to make the battery size smaller in those days in late 90s and early 2000. So that's why we had this kind of compact battery, which is even smaller today. So this is a see-through model. You can see it from outside, and that's basically the same thing as the previous page. NEC also released a commercial product only in the European market in 2003. However, if you release the product later in the market, unless it has something very special, you will not get a big piece in the market, and it also applied to NEC. This product was not very successful, so it stopped after years. Once you have any audio signal related system, it is quite natural to have a corresponding video system. So that's what we did. We extended the system to video, which is called the Silicon View. Now I am showing a similar figure here. Again, memory capacity in megabits versus the recording time. Remember, in this case, because there is a video signal which has much bigger size of the information, it is even harder. For example, for 132 megabyte memory card, you can record up to only 10 minutes. Actually, it was 8 minutes because this is a 30 minute, this is 20, this is 10. It is much shorter than 10 minutes. It was actually 8 minutes. If you increase the video size or the image size, you can record up to maybe 4 minutes. So it's even shorter. So this was not practical in those days, but it was important to show the feasibility. It is important to look. This is what we can do at this moment, and it will be better as the technology advances. This shows a brief schematic block diagram of the Silicon View. In addition to the loudspeaker, we also had a display. The size was originally 2 inches. We also had the slightly bigger version. This is the Silicon View terminal with video and audio playback capability with a 2-inch LCD screen. This is a large, slightly bigger version, a portable model. This is much heavier, but it is much easier to look because of the screen size. When you look into it, this is a print circuit board in it. This is an LSI which we developed to decompress the video signal and the audio signal simultaneously. This is the same chip, but the print circuit board is slightly bigger for the bigger terminal. And again, this is the system for the memory card. And a similar thing is placed on the other side of this print circuit board for this case. So this is a table for specifications. I would like you to concentrate on this power consumption. This is the portable model. The power consumption was 1.7 watt. That means you must have a big, heavy battery, or you need to exchange your battery very frequently. So that's the case in those days when you had the video reproduction capability. It was used for providing information when you visit the museum or any exhibition. This is a video version. We also had the audio-only version, which is much smaller and lighter. But this is an extension of this technology, which you may find something similar today in the market to tell you details of products. This one is called shopping navigation. What this system does is to let you press one of these three buttons, and depending on the button you pressed, different program will be played so that you will get the different information. So this shows a family of the multimedia personal information devices which we developed in the mid-90s. This is an advertisement appeared in one of the major newspapers in Japan. It says, "First in the world, no tape, no motor, the future portable video." And the function of this prototype system was finally implemented in Apple's iPod in the year 2005. So it has taken 10 years until our prototype, until the actual product. Now, let me talk about the impact of the silicon audio on production of this kind of electronic system. This is a simple combination of the decoder plus encoder. And the decoder it consists of peripherals plus purchased LSIs. NEC was lucky to have an LSI division, so we could develop our own LSI. But however, even if you don't have such a division, you can purchase such an LSI in the market. So what does it mean? Anybody can buy chips. Anybody can start manufacturing these terminals. That's the innovation. Okay, so manufacturing revolution took place because of a very small number of the components, and everything was available in the market. Nothing special. No accumulated experience in assembly was needed. So this is the first commercial product of portable all-solid-state portable audio player called MP-Man, marketed by Sehan Electronics Systems in Korea. This is the first version of iPod released in 2001. And when you look at this revolution, it reminds me of the shift from fossil-fueled cars like this. This is Toyota. And these are EVs, electric vehicles, represented by Tesla, US, and also BYD in China. What's the difference? Because of the components. When you look at the components, in this case, the fossil fuel driven cars, you need lots of different types of parts in it. You need to assemble a system with these many components. So that's why you needed accumulated experiences in assembly. However, when it comes to EVs, it's very simple. All you have to have is a battery, you have motors, you have tires. That's it. You don't even need the transmission in the primitive system. So it's very easy to assemble or manufacture EVs. That's why new companies could get into the new market. So that was what happened, and still it's happening. All right. So what is the impact? What are the impacts of silicon audio on personal information devices? Let me talk about it now. MP-Man, the first portable audio players, all solid state one, was released in 1998, 4 years later than our prototype. This is the first commercial solid state audio player. iPod, first version, iPod Classic, was released in 2001. However, it was not all solid state because there was a hard disk drive. There was a mechanically moving parts, so it was not all solid state. The next version of iPod, which was released in 2004, it was not yet all solid state because there was still a hard drive disk. Then what was the first version of all solid state audio player by Apple? That was iPod Nano, released in 2005, which is 11 years later than our prototype. This is a combination of MPEG-4 audio coding technology plus flash memories. So now it is a chip, solid state. And then iPhone came up, which is a combination of an audio player and a mobile phone handset. So it's a simple combination of audio player, mobile phone handset, personal computer, and user interface. That's an iPhone in 2007. The smartphone is a commodity now, and it is actually most promising. Then tablet PCs represented by iPad came out in the market in 2010. What is it? It's an upscale iPhone. The biggest difference is the screen size, which is much bigger in this case. And it's a kind of compromise between smartphone and PC. The size is smaller than the PC, but not as big as the PC display. Keyboard is not equipped. Actually, something like keyboard is provided, but it's smaller. And then after that, smartwatch came out, represented by iWatch. It was the first product released in European market, but Apple followed in the next year, Apple Watch. So this is an iPhone minus display, minus keyboard. So it's very simple, but much smaller. Okay, so let's review how the personal information devices were developed along the time. The original one is, of course, Walkman by Sony in 1979. That was the first one, but all in analog technology. And then we developed the silicon audio in 1904, all solid state. There was no mechanical movement. And then we also developed its video view in the next video version, Silicon View, next year. The first commercial product of all solid state audio player was provided by Seihan Electronics as MP-Man. And then Apple released iPod, but it was not solid state because there was a hard disk drive. It was not yet all solid state in 2004 by Apple. And finally, Apple released iPod Nano in 2005, which was all solid state. And then they also released its video version as iPod Video. And then they tried to combine iPod Video or iPod Nano with a mobile phone handset so that it has communication capability plus multimedia reproduction capability. That is iPhone. Then the display size became bigger as iPod. And then in the other direction, it was made even smaller, smartwatch. And then it continues after that. And this was 2012, already more than 10 years ago from now. And one sad news is that Apple already announced that they will discontinue the production of iPod because it can be done. The same function is provided in an iPhone, or many people today enjoy streaming music. Now, let me talk about the change of the functions, wearable, connected, and sensing. These are personal information devices we developed. First, it became wearable. You can wear a smartwatch on your wrist. And there are devices, so-called hearables, represented by earbuds. Earbuds are not only used for listening to something. There are microphones in it. So it is possible for you to speak to your earbuds, and you can perform communication with it. It also collects some data, your biomedical data from the ear canal. So these additional functions are made available with the hearable devices. Now, these things are connected with your smartphone. So they are connected devices. Why not connect a ring to your smartphone? That is also possible. This is a product called the Oura Ring, available in the US market and some other countries. Basically, this ring collects your biomedical information from your fingers. So they are used as sensors to collect these data like heart rate, sleep record, ECG, electric cardiography, and even blood oxygen level. Actually, this function was very useful after the pandemic period because this is a good indication of how healthy you are. Okay, so this is a summary. I have talked about the history of the personal information devices, starting with the Sony's Walkman. It was implemented completely analog technology, and then we developed its digital version in 1994 as Silicon Audio, extended to Silicon View. So not only the audio, but the video was made available by a terminal backed up with all solid-state technology. And then it has a very important meaning because the number of components has been reduced drastically, and all the components are available in the market. Anybody can join the business simply buying the components in the market. No accumulated experiences in assembly was necessary. That was actually happened. That happened in the personal audio information devices, but it is also happening in the car manufacturing industry today. Those terminals, the information devices have evolved into iPod, smartphones, tablet PCs, and even smartwatches. And now they are widespread. They have widespread applications in addition to players, such as video players and shopping guide on the shelf, and even including sensors, connected sensors to collect your biomedical information. It will perhaps be combined with newly developed AI systems to help control your health condition in the near future. Okay, this concludes my talk. Thank you very much for your attention. If you have any questions, I'd be happy to answer. Any question? Yeah, there are two questions. Yeah, maybe you need a microphone, or I can get closer to you. Is it on? Microphone. Oh yes.
Yeah, it's
now
on.
it is
So
on.
I think you mentioned that you built a first audio prototype from NEC in 1994.
Uh-huh.
I was wondering how come you couldn't go into consumer market?
Okay, that's a natural question. His question is, why couldn't we get into the commercial market even though we developed the first prototype? My answer is, as I already told you, there were issues, mainly the price of the memory and control of the contents. So these were big obstacles. If you cannot see a big market, it is not possible for a company to invest in the development. The memory price was too high in those days. So it was clear that everybody had to wait for some time. That was probably the major reason. And actually, NEC was not a company to do the business in that field. That was not the major business field of NEC. NEC used to make more expensive communication terminals for telephone operators. So for such a company, it was not important to invest some money into unclear consumer market. Consumer market is known to be very, volatile. It keeps changing. It is unpredictable compared to the business like those with big telephone operators. So such a business is predictable. If you invest something, you will get the profit in the near future. But when it comes to a consumer market, it's a kind of a gamble. NEC was not such a company. So that's why there were many follow-up startups, because they don't care for the successful rate in the future. Once they get some investment, they would like to try something new. If it is successful, they will win the market. If not, they will just try something else. So these are the reasons, I believe. Actually, we had the good business chance with the government, Japanese government, to use that device for listening comprehension of the university entrance examination. There is a standardized university entrance examination. There are so many users every year, and it is not easy to keep the same terminal for the next year because of the space of the warehouse. So it was a plan to renew the terminal every year. However, in that case, the price was the problem. We tried to calculate, estimate how much it would be. And then in those days, our estimate was about $20 US. They said it's too expensive to renew it every year. So it was not successful, but it was also possible, or maybe possible, to implement it or manufacture it at a lower price if we try to find a manufacturer in China or Taiwan or Korea or in any other Asian country. We didn't think of any of those. We just tried to implement the product by ourselves and try to estimate, try our best to make the estimated price, estimated cost as small as possible. However, it was not acceptable for the government. So these things are behind the history. Unseen facts behind the history. Thank you very much for your question.
Thank you, sir.
Do you have any other question? Oh, she has one.
Sir, thank you for the talk. It was very interesting, especially because a lot of us did not know how the history evolved. For us, whenever we looked at any audio video device, we always attributed it to either Sony or to Apple. And the fact that the silicon audio is actually the product from where all of the future research was inspired, that was not known. So thank you for showing that to us. And my question is riding on his as well, that at that point there were a lot of limitations because of which you explained, because of which you were not able to get into consumer market. In the current scenario, is there anything that you are what any broad research area that you think could be a good area to look at, which could cater to the current as well as future research aspects?
Um,
It's a general question, just your
Yeah,
thoughts.
yes, I know, but it is very difficult. It depends on what you have in your mind. Well, it can be in any field, it can be on any topic, so it's very difficult to answer, and I don't think of anything specific. If I can, I will, start some business by myself if there is anything promising I can find. But the important thing, as I started with this talk, is that you always review the history because you can now see everything, what happened and why. You can perform analysis, but it is not possible to see. You cannot look ahead and you cannot say something definite because it has not yet happened. So it will not be the case. There may be something else. So it is next to impossible to answer anything like that. But it also means that the chances are much better. You can do whatever you believe is promising. So give it a try because you are still young, and I hope you will succeed in whatever you believe in. Thank you very much.